to continue our discussion of rational functions today. Your quiz 5 that I gave you last Wednesday is due, so just put that in your folder before you go. Other than that, we have another take-home quiz coming up. I will give it to you next week on Wednesday. And then we've got test 3 coming up after that. So we are approaching the end. I'm going to have you start on the preview exercises, and then we'll spend a little time going over them. I'll give you five minutes or so to work through these. All right, so last class we studied the behavior of two new parent functions, 1 over x and 1 over x squared. We did a lot of work with them. We figured out what their asymptotes are, what their end behavior is, and we were able to graph many functions by transforming those two parents, but we won't be able to do all of them that way. Okay. So remember that both of these parent functions have a vertical asymptote at the value of x that is excluded from the domain. So in each of these cases, when x is 0, you get something undefined because you have a 0 in a denominator. So x equals 0, vertical asymptotes. All right, so I want to label each graph with its formula. This one on the left, is it 1 over x or 1 over x squared? Y equals 1 over x, yep. And you can tell because you have some positive y values and some negative y values, right? Because when you plug negative x's in here, you're going to get negative y's. So that means that this one has to be 1 over x squared. And no matter what x you plug in, positive or negative, the y value is always going to be positive here. Because when you square something, you always get something positive. So that's why the whole graph lives above the x-axis. All right, so in general, how do you find vertical asymptotes of a rational function? Missing a letter there, r of x. Whatever makes the denominator 0. Yeah, so I would take the denominator, which I called q of x here, set it equal to 0, and solve it. All right, now I want to find the equations of the asymptotes, the vertical asymptotes in each graph. Okay, so vertical lines that the graph approaches but doesn't touch. Okay. This first one, it doesn't have any vertical asymptotes. The next one, this pink vertical line, what is its equation? X equals 2. A lot of you were trying to write a formula for the rational function and doing it correctly, but you just got to read the question. Just wanted an equation of the vertical asymptote. All right, and then this other one, it's got two vertical asymptotes. This first one is at x equals -2, and the next one is at x equals 2. Can a graph of a rational function intersect a vertical asymptote? No, never, because the graph is undefined there. The function is undefined there, so it can never cross. Okay. And how do you indicate a vertical asymptote on a graph? Dotted line. Good. All right, so let's look at the function x squared minus 9 over x plus 3. What x values are excluded from the domain? -3, right? Your denominator has to we have to make sure that it cannot be 0. So that means that I have to exclude -3 is excluded from the domain. So now I want to reduce this rational expression, rational function, to lowest terms. So that means factor and cancel. X squared minus 9, how does that factor? Okay, so this factors to x plus 3 times x minus 3 over x plus 3, and then my x plus 3's cancel. And I am left with just x minus 3. Okay. And what does the graph of x minus 3 look like? It's a line, yeah. It's a line. What's its y-intercept? -3. Do you guys completely forget how to graph lines? Y-intercept's -3. What's its slope? 1. Yeah. This is a line. Slope is 1. Y-intercept is -3. Right? So we can graph it. It's just a line. Right? So this is a line, and y-intercept at -3. So I can put that on there. And then my slope is 1, which means it's got to go up up 1 over 1. I just did that a couple of times. Up 1 over 1, get some points that are far apart, and then I connect them. Now, what makes this line, though, a little bit different than x squared minus 9 over x plus 3? In general, this equals this, except for one value of x, -3, right? You can put a -3 in here, you'd get -6, right? But you can't put it in here because you get an undefined expression. So we got to go to when x is -3, right here. You got to go down to the graph, and you got to put a hole. Should erase the -3, -6. You got to have a hole there. So this rational function actually turned out to be a line with a hole in it. Yeah, it just skips it. The hole happened because it's a place where the denominator was 0, right? But then it turned out that that's not a vertical asymptote in this case because the factor that made the denominator 0 ended up canceling. So that happens whenever you have the same factor on the top and the bottom that makes both the top and bottom 0, then you get a hole. Okay. Where is it? It happens when the x value is -3, the value excluded from the domain. So I just went to my graph. I went to x equals -3, down to my line, and inserted a hole.
So there is no vertical asymptote.
Yes, there's no vertical asymptote, but there is an excluded value. So this is the conclusion. Okay. X values that make the denominator equal 0 could result in a vertical asymptote or a hole. Right? So if you have a value that has to be excluded from the domain, it could be a vertical asymptote or it could be a hole in the graph. You get a vertical asymptote if the x value makes the denominator 0 and not the numerator. Okay. Oh, I guess I don't need that. It still makes sense. Vertical asymptote if the x value makes the denominator and not the numerator equal to 0. But you get a hole if that x value makes both the denominator and the numerator equal to 0. So think about that -3. If you put -3 into the original function, x squared minus 9 over x plus 3, you get 0 on top and 0 on the bottom. So you get a hole.
Wait, can you say that again?
If you plug -3 in here, -3 squared minus 9 over -3 plus 3, that results in 0 over 0. Both the top and the bottom give you 0. That means you have a hole in the graph.
Okay.
If just the denominator were 0, that would be an asymptote.
Okay.
All right. So the end behavior of a rational function determines where or if there's a horizontal asymptote. Okay, so now we're switching to horizontal asymptotes, and this is end behavior. Okay. So let's analyze the end behavior of a few rational functions and see if we can develop some conclusions. So I've got 9x squared over 3x squared plus 1, and I graphed a picture of it below. As x approaches infinity, what does f of x approach? Nope. Nope. 3. As the x values get really big, the y values are approaching this value of 3. The y values are approaching 3. And as x approaches negative infinity, as you go really far to the left, what are the y values of this graph doing? They're approaching 3 also. So we can see it graphically that they're approaching 3. Let's look at the formula and see if we could figure out how that 3 comes about. If I were to plug in a trillion or a quadrillion or a Google, right, into this function, does that +1 really matter? No, it's so tiny and insignificant compared to a quadrillion, right? So this, when x is really big, this is actually going to look like 9x squared over 3x squared. That +1 makes almost no difference at all. And then the x squareds cancel, they're the same, right? So it's 9 over 3 is 3. That makes sense? All right, so we can see it graphically, and we can see it algebraically. What happens to that formula when x is really, really big? All right, let's look at the function g, 9x over 3x squared plus 1. As x approaches infinity, as I move really far to the right, what's happening to the y values of this graph? They're approaching 0, declining, yeah. And as I go really far to the left, what's happening to the y values of this graph? Also approaching 0. From below 0 this time, but they're still approaching 0. All right, so we can see it graphically. Let's look at the formula. Again, if I'm plugging in huge x values, like a quadrillion, right? The biggest x value you can think of, that +1 in the denominator is useless. It means nothing. It's so tiny compared to the large, large number you're plugging in that when x is really, really large, this is basically 9x over 3x squared. 1x cancels, right? And I get 9 over 3x. And then I'm plugging in giant, giant numbers, right? So my denominator is getting really, really big. So what happens to a fraction's value when the denominator gets really, really big? It gets smaller. It's going to go to 0. Does that make sense? So that's how we can think of that algebraically. All right, one more. 9x cubed over 3x squared plus 1. As x goes really far to the right, what's happening to the y values of this graph? They're going up towards infinity. And as we go really far to the left, what's happening to the y values? Negative infinity. Let's see if we can think about this algebraically, not just graphically. So again, plugging in really large values for x, biggest values of x you can think of. That +1 means nothing. It's insignificant. So this is approximately 9x cubed over 3x squared. And when I cancel stuff, this is going to reduce to 3x. Right? And what happens to 3x when x gets really big? It approaches infinity. It just gets bigger and bigger. And when x approaches negative infinity, this will also approach negative infinity. Does that make sense? All right. So finding horizontal asymptotes. Here's your conclusion. We just found horizontal asymptotes without knowing these rules. So these rules are very handy, but you can always just sort of think about what happens as x gets really big. Okay. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote. That's this middle case, right? The degree of the numerator was 1, the degree of the denominator was 2. The degree of the numerator is smaller than the degree of the denominator, so my end behavior is just the x-axis, y equals 0. If the degree of the numerator equals the degree of the denominator, like in example 1 here, they were both squareds, they both had a degree of 2. In that case, the asymptote happens at the ratio of the leading coefficients, so the 9 over the 3, right? That's where we got the asymptote from. Just look at the ratio of leading coefficients. Yes?
You canceled out the x squared.
There's no 4.
Oh, I mean, taking 1 out, 3 plus.
Oh, we just dropped the 1? Yeah, because we said we're plugging in, imagine plugging 1,000,000 in there.
Yeah. Okay.
So that's going to be 9 times 1,000,000 squared over 3 times 1,000,000 squared plus 1. The +1 is just so small that it doesn't even, it's so insignificant, we can just ignore it. Okay. All right, and then my last possibility is when the degree of the numerator is greater than the degree of the denominator. So that happened in my last example. My degree on top was a 3, the degree on the bottom was a 2. So the numerator was greater than the denominator. That meant I had no asymptotes. My end behavior was infinity or negative infinity. So there's no horizontal asymptote in that case. Okay, a couple of fun facts about horizontal and vertical asymptotes. A rational function may have several vertical asymptotes, but it can have at most one horizontal asymptote, 1 or 0 it can have. And although a graph can never intersect a vertical asymptote, it may cross its horizontal asymptote. Okay. The horizontal asymptote only governs what happens as at the end behavior, to the far right and the far left. In between there, it might cross. It might cross the horizontal asymptote. So here are some general steps for graphing a rational function that's not just a simple transformation of 1 over x or 1 over x squared. So we did ones like that last class. If it's not easy to transform one of those, this is our process. 1, make sure the rational function is fully reduced, right? Do all the factoring and canceling you can before you start. So that is factor and cancel. Okay. Then check if there's any symmetry, because if you have some symmetry, you really only have to graph half of it. And then you can just copy the other half using symmetry. Step 3, find the y-intercept, if there is one, by plugging 0 in for x. Step 4, find x-intercepts by setting the numerator equal to 0 and solving. You only have to set the numerator equal to 0 because any fraction, the only way a fraction can equal 0 is if its numerator equals 0. Find vertical asymptotes by setting the denominator equal to 0. Horizontal asymptotes by comparing the degree of the numerator and the denominator. And then plot at least one point between and beyond each x-intercept and vertical asymptote. Connect the points using the asymptotes and symmetry as a guide. All right, so I've got a couple of examples we can do together. So step 1 was make sure it's completely reduced. So we should do all the factoring and canceling we possibly can. So I'm going to say 2x squared, that cannot be factored, but x squared minus 9 is x plus 3, x minus 3. Can I cancel anything? No. Okay, so I tried to reduce it, it doesn't reduce. Step 2 was check for symmetry. Okay. So to check for symmetry, I plug in a negative x, right? So this is going to be 2 times negative x squared over negative x squared minus 9. So just in my original function, I replaced each x with a negative x. Okay. And what do you get when you square negative x? Positive x squared. So this is 2x squared over x squared minus 9. That is my original function, right? I got the exact function I started with back. So what does it mean if f of negative x is the same thing as f of positive x? What kind of symmetry? Even symmetry. Or y-axis, whichever one you want to call it. Okay, so I have even symmetry. Let's see, what was my next step? Step 3, y-intercept. Okay, so the y-intercept you get by plugging 0 in. So that's 2 times 0 squared over 0 squared minus 9. Zero over negative 9, which is 0. 0 over anything is 0. So I've got a y-intercept of 0. So I can put that in right now. Yep. So the next step is to find x-intercepts, and you can do. So 2 times 0 squared is 0, right? So you get 0 on top. 0 squared minus 9 is negative 9. 0 divided by anything is 0. All right, so now I got to look for x-intercepts. Just gonna scroll down a little bit here. X-intercepts are found by setting your numerator, in this case 2x squared, equal to 0. You just have to set the numerator equal to 0 to get x-intercepts. So what value of x makes this true? The solution to this equation? 0. X equals 0. So that's also the same point, x equals 0. All right, so I have x and y intercepts. What's the next thing on the to-do list here? X-intercept, y-intercept, vertical asymptotes. Set the denominator equal to 0 and solve. So my denominator is x squared minus 9. So when I solve that, what do you get? Plus or minus 3, right? Yeah. So those are my vertical asymptotes. X equals positive and negative 3. So I'm going to put them in as dashed lines. All right, so my next step is to think about end behavior, which would tell me a horizontal asymptote. So we compare the degree of the numerator and the denominator. They're the same, which means my horizontal asymptote is the ratio of leading coefficients, 2 over 1. Y equals 2 over 1 is my horizontal asymptote. So I looked at my original function, right? And I said the degree of the numerator and the denominator are the same. They're both squareds, right? So then I just take the ratio of the leading coefficients. There's a 2 over 1. Yeah. Coefficient, the number attached to the x squared. You just take a fraction. So that's our leading coefficients. Yeah, that's one of the 3 rules. There's 3 possibilities for horizontal asymptotes. When the degrees are the same, you just take the leading coefficients. So y equals 2 is my horizontal asymptote. All right, and then I believe my last step is to look at, I need to plot some points. Plot at least one point between and beyond each x-intercept and each vertical asymptote. So I've got one point here between 2 vertical asymptotes. And I know that as the question is, which direction do these things go, right? It could be that it goes like this, or they could both go down. We know that they have to approach the asymptotes, but I don't really know what direction they're going to approach the asymptotes in. So I need some points. So let's see, what happens if I plug in, say, positive 1 in my original function? So here's step 7. F of 1, yeah. So that would be 2 times 1 squared over 1 squared minus 9. So that's 2 over negative 8, negative 1/4. So that means it's negative, right? So I would do 1, negative 1/4. I get a point right there. So now I know what direction my graph is going to approach the asymptote with. It's going to go like this. And because I know I have even symmetry, I know the other side is going to do the same thing because I have to have y-axis symmetry. All right, now I need to know what happens on either side of 3 and negative 3. So let's pick another number. Maybe we'll pick 5 and plug 5 into my function. So f of 5. Now I need to know what happens over here and over here. So I just picked an x value of 5. I picked a random x value on the other side of 3. Okay. So I'm going to plug a 5 in, get a y value. So this is going to be 2 times 5 squared over 5 squared minus 9. So that's 50 over 16. I don't know, what is that?
25 over 8.
Yeah. Okay, I'll get a calculator.
3 and 8.
3.125. Okay. All right, so 5 comma 3.125. A little bit more than 3. And then since now that I have that 1 point, I can use my asymptotes to guide what the rest of this thing is going to do. It's got to approach my horizontal asymptote with the end behavior, and it can't cross the vertical asymptote, so it has to go like that. And then because I have y-axis symmetry, I can just copy that onto the other side of the graph. So I'm going to have negative 5, a little bit more than 3, and copy what I did on the right. So there's my rational function.
Oh,
That's it. Only 7 steps. Oh. All right. I think we should do one more together before you try them on your own.
How did you get the y equals 2 over 1?
The y equals 2 over 1 came from looking at the original function. Hey, quiet. Okay, so I compared the degrees, right? And there's 3 cases. In this case, the degrees are the same, right? So I go back to my list of rules. If the degree of the numerator equals the degree of the denominator, okay, then y equals a over b is a horizontal asymptote, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. So my leading coefficients were a 2. There's a 2 on the x squared in the numerator, and there's a 1 on the x squared in the denominator. 2 over 1. All right. Yeah. Okay, let's do another one. Okay, so 4x over x squared minus 1. So step 1, factor and cancel if possible. So f of x is going to be 4x over x plus 1, x minus 1. Anything cancel? Nope. Okay, so I'm done there. Step 2, check for symmetry. So I'm going to plug in a negative x, and I get 4 times negative x over negative x squared minus 1. 4 times negative x is negative 4x. Negative x squared gives me positive x squared minus 1. Is that the exact function I started with? No. Is it the exact opposite of the function I started with?
Yes. Yeah.
Yeah, because you can put a negative sign anywhere in a fraction, top, bottom, or in front. So this is actually negative 4x over x squared minus 1, which is negative f of x. So what kind of symmetry do you have when f of negative x equals negative f of x? Odd or origin symmetry. Okay, step 3, I think, was y-intercept?
Yeah.
Okay, y-intercept, you plug 0 in for x. F of 0 is going to be 4 times 0 over 0 squared minus 1, which is 0. All right, I can graph that. Step 4 is x-intercepts, which means just set your numerator equal to 0. and you get x equals 0. So that's this point again. Step 5 was vertical asymptotes. And you get that by taking your denominator and setting it equal to 0. So that would give me plus or minus 1. So I can put those in. Yep, vertical asymptotes at plus or minus 1. And then I got to check the horizontal asymptote, step 6. So I have to compare the degree of my numerator to the degree of my denominator. So this is 4x over x squared minus 1. Right? Which one is smaller? The numerator, right? So when the numerator is smaller, what's my asymptote? 0. Yeah. You can also just rethink about this. If x is really, really big, the minus 1 almost doesn't matter, right? It's so insignificant compared to a billion or a trillion. So this is approximately 4x over x squared. You can just drop the minus 1. And then that reduces to 4 over x. And when x gets really, really, really big, that denominator will get really, really big. And when the denominator of a fraction gets big, the value of the fraction gets small. So that goes to 0. So my horizontal asymptote is y equals 0. And that's the x-axis. Yeah. Okay, so then I have all my asymptotes in place. I have my intercepts in place. Now I just have to plot some points. My vertical asymptotes have divided my plane into 3 regions, right? I've got the left side of my asymptotes, I've got between the 2 asymptotes, and the right side of my asymptotes. So I'm going to plot some points in each of those regions. So let's look at, pick a point to the left, like maybe -5. F of -5 is going to be 4 times -5 over -5 squared minus 1. So it'd be -20 over 24. So that's not quite -1. So like right there, -5, -1. And then I know what the rest is going to happen. It has to approach my asymptotes. So I just needed this one point to know what it's going to look like. It's going to approach the asymptotes, but it can't cross either of them. All right, and then in between my 2 asymptotes, I already have 1 point, but I'm going to need 1 more in order to know whether this is going to go up or down or 1 of each. Okay, so maybe I'll plug in a half and -1/2. F of 0.5, that would be 4 times 0.5 over 0.5 squared minus 1. So that's 2 over -3/4, which is 2 over 1 times 4 over 3, -8/3, almost -3. You can just use your calculator to get that number. I plugged in 0.5, yeah. I just picked a random x value to the right of the point I had. So, and to the right, which was at 0, but I didn't want to go past 1 because that's where my asymptote is. So halfway between was 0.5. So I have 0.5, almost -3. Right, so I know that this side has to go down like that. Yeah, we know we have odd symmetry, so I now have enough to finish my graph, right? If I have origin symmetry, the other piece of this has to go up. And then the mirror image of this piece that I drew over here already in quadrant 3 has to be reflected up here in quadrant 1. So this was -5, almost -1. So I'm going to have +5, almost +1, and then approach the asymptotes.